Welcome to another video on wastewater treatment of urban sanitation series. There are broadly three categories of wastewater treatment system, which are aerobic treatment, anaerobic treatment, and fecal sludge management, which shall be outlined in the upcoming slides. In aerobic treatment, the COD fractionation is important to understand the wastewater to be treated. The volatile suspended solids (VSS) or mixed liquid suspended solids (MLVSS) in a reactor of an activated sludge process contain ordinary heterotrophs, which consume biodegradable soluble and biodegradable particulate organics. When these organisms die, they leave behind unbiodegradable particulate called the endogenous residue (XCOHO). Organic components of suspended solids (VSS) or XVSS accumulate in the reactor as three components: XOHO, XeOHO plus XU, where XU is unbiodegradable particulate organics. Unbiodegradable particulate affects the sludge accumulation in reactor and daily sludge production, whereas unbiodegradable soluble affects the filtered COD effluents in the reactor. The activated sludge in the aeration tank, which also receives recirculated sludge from clarifier, where majority of organisms are ordinary heterotrophs. They can be better understood with kinetic and stoichiometric constants, which are specific yield coefficient YOXHO, specific endogenous mass rate BOHO, unbiodegradable fraction of OHOs FXeOHO, and COD/VSS ratio of the sludge. These constants are temperature dependent as shown in the table. Activated sludge process system description. All the aerobic biological treatment systems such as trickling filter, aerobic lagoon, extended aeration operate on the same principle. They differ by system constraints in the condition under which the biological reaction occurs. System constraints include mixing regime and sludge retention. The system can be described through steady and dynamic model. Steady-state model is employed to describe performance of the system design parameters such as reactor volume, recycle, waste flow, average oxygen utilization rates, and values of various concentration in reactor. In activated sludge theory, the volume of reactor per unit volume of influent flow is known as the nominal hydraulic retention time. Sludge abstraction directly from reactor leads to a method of control of the sludge age, called the hydraulic control of sludge age or sludge retention time, which has significant advantage for system control compared to abstracting wastage via the underflow. In anaerobic treatment, the anaerobic degradation of organic polymer takes place in four stages when there is low redox potential available. The four stages are hydrolysis, acidogenesis, fermentation, acetogenesis, and methanogenesis. In hydrolysis of biopolymer, the hydrolysis of protein, polysaccharides, and fats takes place. In acidogenesis, the anaerobic oxidation of amino acids, sugar, higher fatty acid, and alcohol take place. In acetogenesis, the formation of acetate and hydrogen gas from intermediary product occur. Also, formation of acetate due to homoacetogenesis takes place. The last step in anaerobic digestion, that is methanogenesis stage, takes place due to methane formation due to acetate as well as hydrogen and carbon dioxide. There are different configurations of anaerobic digestion, which are broadly categorized as completely mixed, physical retention, immobilized biomass, and enhanced contact to better understand the anaerobic digestion. The different systems are namely as shown in the figure are anaerobic pond, imhoff tank, and completely mixed anaerobic reactor. To enable an anaerobic reactor system to accommodate high organic loading rates for treating a specific wastewater, the following conditions should be met. High retention of viable sludge in the reactor under operational conditions. Sufficient contact between the viable bacterial biomass and wastewater. High reaction rates and an absence of serious transport limitations. The latter refers to both substrates and intermediate reaction products. The viable biomass should be sufficiently adapted and/or acclimatized. Considering the low microbial growth rates under anaerobic condition, thus long SRT's biomass adaptation can take very long periods of time. Prevalence of favorable environmental condition for all required organisms inside the reactor under all imposed operational conditions, focusing on the rate limiting steps should be taken. Fecal sludge management or on-site sanitation, either as an intermediate or permanent standalone solution or in combination with sewer-based systems, the appropriate and adequate management of fecal sludge deriving from on-site sanitation technology is imperative for the protection of human and environmental health. The different components of it are containment, emptying, transport, treatment, and recycle and reuse. The treatment of fecal sludge management can broadly be separated by the type of treatment into solid-liquid separation, dewatering, and stabilization/further treatment. The different treatment technology as classified is shown in the table. The end use of treated fecal sludge can be as soil conditioner, in irrigation, as proteins, building material, biofuels, fodder, and plants. The fecal sludge characteristics differ greatly from wastewater and have a direct impact on the efficiency of treatment mechanism. Important properties of sludge to consider include stabilization, organic load, particle size and density, dissolved oxygen, temperature, pH, water content, and viscosity. These are the parameters which should be considered. Planning citywide sanitation strategy for fecal sludge management is important due to diverse level of service and patchwork of uncoordinated and independent stakeholders managing various activities. FSM planning aims to transform such complex situation into a well-organized and coordinated management framework expressed initially as citywide sanitation plan or citywide sanitation strategy. The figure shown summarizes the current situation of fecal sludge management, thus enable as a reference tool to measure impact after FSM strategy is adopted. The technology being selected for treatment, the technology is selected based on the local context and the proposed end use.